around this video, I'll explain the diprotic titration. Okay, so first thing first, we need to understand there are two types of diprotic titrations, at least the ones that are going to be tested. Okay, so one will be if you have a diprotic acid, right, and then you're titrating with a strong base. And we have also another situation the other way around, right? So if you have a diprotic base and titrating with a strong acid. So then that actually was one of the example question we did. Okay, so now I'm going to actually talk about the other one, since we already went over that diprotic base with a strong acid titration during the class. So now I'm going to explain the other way around throughout ask yourself question. Okay, so now I'm going to share my screen and then let's look into that. Okay, so this is the ask yourself question. Okay, so now let's start reading the question and see what's going on. Okay, so first thing first, the question mentioned a malonic acid. Okay, and then we're titrating it, or the titration goes with sodium hydroxide. Okay, so then you go, oh, where I put that acid, where I put that base. Okay, so now if you do have the volume and the concentration, right, then we know that goes into the element flux, right? Because that's something you put in because you already know how much it is, right? The one you put into the burette, that's something we don't know how much we need to use. We'll figure out throughout the titration, right? Okay, so that's that. So now we know inside the burette we'll have sodium hydroxide, okay, and then we know it's 0.1 molar. We'll figure out how much we need to use, okay, and then for the in the element flux we'll have that acid, okay, so the acid amylase. Okay, so that's 50 ml, 0.05 molar. Okay, so then you go, what kind of acid is this? Okay, so then you go, I don't know. And then of course, for the question as on the quiz or exam, I will give you information like this, and then to help you figure out what kind of acid. Then you go, what do you mean? Right? We have monoprotic situation, we have diprotic situation. Okay, so then which one that will be? Right? If you see two K values, that's quite straightforward. One's gonna be K1, the other one's for K2. So we do have a diprotic acid situation. Okay, and then I don't have a chemical formula. What do I do? Okay, so then you can use this generic form. Have diprotic means so I have two protons. Okay, so I H2A. So then now, right, by rating, we gather the information like this. Okay, so now I have a titration, and let's see what's the first question it's asking us. Sub question A, right, part A is asking how many milliliter ml of the titrate. You go, which one is the titrate, right? The one we don't know how much we're gonna use, right? That's the one in the burette, so then that's sodium hydroxide. Okay, so then it's asking to reach each equivalence point. You go, what do you mean each? Remember, there are two protons, right? When you neutralize the first one, right, and then you get the first equivalence point. When you neutralize both, then you have the second equivalence point. Okay, so now we can talk about how we do this calculation. Okay, so first thing first, I'll say we can always go to write down the equation because there is a reaction happening. So balance equation always should be helpful. Okay, so H2A reacting with this sodium hydroxide. Okay, product should be salt and water. So we'll have salt and this. But then is this correct? Is it? You probably know, right? Because look, there's two protons, which means this will be positive one, that's negative two, right? Okay. So again, if there's negative two, this is positive one. Will that work? No, we need a subscript. Okay, so over here. That's also why when you have diprotic, you need to know it's not going to be 1-to-1 ratio, right? If you're titrating with sodium hydroxide 1A group, right? Only one hydroxide, right? Okay, so that's that. And then you also, of course, have water. Okay, so then we're going to balance that. Okay, so then you have balance equation. We realize this reaction goes by 1-to-2 ratio. Every 1 mole of this acid, you need 2 moles of the base. Okay, so then once they completely react, that's when we reach the second equivalence point. During the lecture, I introduced another way, right? So you can calculate the moles, and then when you reach the first equivalence point, that's going to be 1-to-1 ratio. Now I'm explaining from another way, looking into this. I hope this is helpful. So then whichever way you think is helpful, so then that works out. Okay, so now I'm going to talk about, right? By stoichiometry, we'll understand, right? So when they're going to completely react with each other, that's 1-to-2 ratio. And then we know information for the acid. Okay, so we'll have the volume, we'll have the concentration. We can calculate how many millimoles will be there. Okay, let's do the calculation. Okay, so H2A, so we can use that 50 multiply 0.05. So this gives us 2.5 millimoles of the acid. Okay, so again, we know how the acid is related to the base. Okay, so this much acid need how much base set up, right? This given desired cases, every 1 mole of this diprotic acid will need 2 moles of this base. Cancel that out. we'll get 5 millimoles of this certain hydroxide. Okay, so you need double the amount to reach to neutralize both those protons. Okay, so then again, now I am actually calculating VE2. Okay, just so again, I'm introducing a different way of looking into this, how to calculate both the volume needed reach each equivalence point. Okay, so VE2 because why is VE2? Because we're calculating based on completely reacting with each other. Okay, so now you have 5. If we know you have 5, and then how do we calculate the volume we need it? Okay, so this VE2 will equals to 5 millimoles divided by its concentration. What's its concentration? It's 0.1. I'm also color coding. Okay, so it's 0.1. Okay, so you go, what's molar? Let's translate. It's mole per liter. That cancels out. Unit will be milliliter, and this comes out as 50. Okay, so you need 50 ml to reach the second equivalence point where you completely reacted the acid with the strong base you're using to do the titration. Okay, so that's V2, and then if you understand that, then what's the VE1? That's halfway, right? Okay, so then VE1 will be half of VE2, will be 25 ml. Okay, so again, during the lecture, we calculate VE1 first by knowing 1-to-1 ratio. Okay, so then you doubled VE1, get to VE2. Now we did the other way around. I hope everyone understands this. Okay, so now you have VE1 equals to 25, VE2 equals to 50. Okay, so now you go, now what? Okay, so now what is that? As I mentioned, I will be providing the whole equation. Okay, so to you. Okay, so now actually I'm gonna start write the equation since this is a video. I have time, right? So then I'm gonna repeat equations. Okay, so then we can look into that. Okay, so give me a second. So then I'm gonna start to put it on here. Okay, so we're titrating. Okay, so remember the whole set I'll be giving to you. Okay, so now if your titration of H2A with hydroxide, that VB equals to 0. So when you didn't add anything yet, then you're just finding the pH of H2A. Okay, so are we able to do this? I think so, right? Okay, so then let's see, did the question ask us? Yes, right? VB equals 0. That's you didn't add any that strong base in, you just have acid. That's easy, right? Okay, so then that's that. Okay, so A is VB equals to 0. Okay, so we only is that H2A. Okay, so then you go, oh, how do I do this calculation? You're gonna treat it as a monoprotic and do the calculation. Okay, so now let's do that. Okay, so treat this as the monoprotic acid and then set up the shortcut. Okay, I believe we know the shortcut, right? Okay, so now let's do the calculation. Okay, so now we're gonna use that our formal concentration of that, right? Okay, so that's H2A have releasing 1 proton. Okay, and what goes onto the double hydrido? That will be Ka1 or K1, right? Okay, so now let's do the calculation do the shortcut 0.05 minus x, and x. You go, where did you get this? That's our concentration. You have to remember when you do set up equilibrium ice table, that's concentration. And for the ice, it's 0.05. Don't use the wrong number. Okay, so you have to know when to use moles, when to use concentration, okay, because you're tracking of different information. Okay, so that's that. And then now let's do x squared over 0.05 minus x. And then giving you the Ka1 or K1, and then that's given from the question, 1.42 times 10 to the power of -3. You go, oh, this doesn't sound small approximation will be applied. Again, I'll just give you the answer at this moment, but as an assessment question, I will give you a value which will, that small approximation will be applicable, so that it's easier for you to do the calculation, do the math part. Okay, so I'll just show you what the x will be solved as 7.75 times 10 to the power of -3. Okay, which equals to the concentration of proton, and then take a negative log, we can calculate pH equals to 2.11. Okay, so that's your first data point where we didn't add any of the base here, it just the acid inside this element flask, and then its pH, just a weak acid. And that's a diprotic, we treat it as a monoprotic. That's how it works. Okay, so then that's where we started, and so then that's that. Okay, so now let's see when you add 12.5, what is it? Okay, so then you go 12.5, where are we? Oh, where are these numbers? What are they matching with? Okay, so now let's think about it, right? We had when you add, we already calculate, right? That's our first equivalence point, and that's our VE2. That's the second equivalence point. Now look at the values. We can do the observation, right? So what's this? This is half of the first equivalence point right here. And then what's this? This 3/2 of the first equivalence point, and then that's your second equivalence point, and this will be what? After equivalence point. Okay, so now we'll be able to use all the equations given, right? Okay, and then just do the calculation. Okay, and then many of the regions actually calculation, I'll say, is not right not a must, because if you know what we're dealing with, the answer is quite straightforward. Okay, so now if we be adding 12.5, we already understand this is our half, right? Half of the first equivalent point. We're halfway to the first equivalence point. You go, what's going to be there? And then what's going to be very helpful is the ladder diagram. Okay, so the ladder diagram is over here. I'm gonna draw this for you. Okay, so remember we have starting from H2A, from the most acidic form, and then when you donate 1 proton, we have HA minus, that's our intermediate. Then when you donate a second proton, we get to the most basic form. Okay, and then on the bottom, what do we have? This is our PK1 or PK1. This is our PK2. Okay, and then top, you can use pH to compare what we have. As I said, for Diprotic, I really give you all the landmarks, usually the ones it's easy to figure out. Okay, so now that's for that, and then you go, oh, but at this point, what do I really have? What does that mean, the half equivalence point? Okay, so the first equivalence point, you go, where is gonna be? Okay, so the first equivalence point is actually over here. Right? Okay, so you will have your major species as your intermediate. Okay, so that again, right? What was the first equivalence point mean? That you neutralize, right? You neutralize the first proton donated by this diprotic acid. Okay, so then we will turn those into, and then we end up with this HA minus, which is the intermediate. Okay, so now that's the first equivalence point, but we're only at half of the first, right, equivalence point. So then take a guess, we're halfway to the first equivalence point, and then there's just 1-to-1 ratio mixture of this and this. So then you're over here, right? You're halfway to the first equivalence point. Okay, so let me just label that. Okay, here, that's your VE1, right? Okay, so okay, so now if you know, okay, I'm halfway to the first equivalence point, I have 1-to-1 ratio mixture of this H2A and HA minus. Okay, so then again, we know this is a landmark pH just equals to PK1. And right, why is that? Because you use Henderson isobar, right? Okay, so if you have just 1-to-1 ratio, what happens? The log part turn into 1-to-1 ratio, the ratio is 1, log 1 is equal to 0, so pH just equals to PK1. Okay, and PK1, you go, oh, do I know PK1? You know Ka1, are we able to calculate PK1? Take a negative log for this value. Okay, so take negative log, I'm gonna give you the values. So over here, let me get some space. PK1, after you take negative log of both K values, K1 is 2.847. Of course, you can, when we report our pH, we suggest it just to keep 2 decimals, so that'll be 2.85. Okay, so then you go, oh, looks like from 2.11, the pH, right, is changing. Okay, so you go, but it's a buffer, so not changing dramatically. That makes sense. Okay, so now let's keep on going. The next landmark, or next, the question is asking. Okay, so still B, but let me just okay, so then there's 25. So the VB at is 25 right now. Okay, again, we know this is at the first equivalence point. Okay, so first equivalence point, you have this H2A, right? Okay, so you converted this H2A, okay, and into HA, right? Okay, so now this is what? This is a intermediate form of this diprotic acid. And we also learned, or actually we got to test it, right? How to calculate intermediate form of their pH. pH equals to approximately equals to half of the PK1 plus PK2. You go, oh, what was PK2? I showed you the PK1 value. Of course, you can take negative log of K2. Okay, it's over here, right? Okay, take negative log of that, you will get 5.696. So let me label that. Okay, so PK2 equals to 5.696. So now let's do that calculation. So then the pH at this point, first equivalence point, will equals to 4.27. You go, okay, so that sounds good. Okay, so that's VB equals to 25. You go, what's next? Next, the question is asking when VB equals to 37.5 ml. You go, where are we? Okay, so we're at 3/2 of the VE1. Okay, so at this point, your half let's look at our map. Okay, half of this converted to A2 minus. Okay, so let me write that down. Okay, half of this HA has been converted to A2 minus. Okay, so now you go, oh, now what? If half of this converted to that, you have 1-to-1 ratio of HA minus and A2 minus. We'll have, well, again, another landmark, right? So over here, pH equals to pK2. Because it's 1-to-1 ratio, remember, log of 1 equals to 0. pH is equals to pK2 at this point. Okay, that's easy, right? This is 5.70. Okay, so now again, coming from this value, at this landmark over here, right? That's your pK2. That's the value we calculated based on Ka1. I'm sorry, based on the Ka2 value. Okay, so now that's that. Okay, so now let's do the next landmark or the next volume. Next volume will be 50. Okay, so 50, we're at VE2. Okay, so the second clearance point. At this point, where we are finally at, we converted where we're donated both protons that have been neutralized. Now you just have everything converted to A2 minus. Okay, so everything you converted H to A, that's that, has been converted completely to A2 minus. Okay, so now that's what we have, and we're gonna do the calculation. Oh, how do I calculate? It's all of that. So now what do I need? Okay, so what do we need? We need formal concentration. Then we can set up the, right, what's going on with it. Okay, so then let's calculate its concentration. Okay, so we call it as the formal concentration. What's the formal concentration gonna be that? Okay, so you go, I don't know. Then the question will be, how do I calculate concentration? Moles over, right, volume liter of the solution. Okay, so then how many moles do we have? You go, I don't know. Let's see the equation, right? I'm gonna bring the equation over. Or let's look at over here. Okay, so we had how many moles? 12 millimoles, right? Of this is 1-to-1 ratio. So all of this will go into the same amount because it's 1-to-1 ratio. Okay, so it's also 2.5 millimoles calculation. I'll be using this. Okay, so I'm gonna actually change the color now. Okay, so let's bring that in calculation. So everything is 1-to-1 ratio. So all of this 50 ml of this 0.05 molar of the acid, all converted 1-to-1 ratio to A2 minus. Okay, now the question will be, what's the volume now? Right, this always have been the question I keep on asking you, right? So you go, I don't know. Look, I started off with 50 ml. At the second equivalence point, how much of the base I added is also 50. And look at our second equivalence point. Okay, so then it's going to be 50 plus 50. So then that's the volume at this moment. Okay, so of course we can cancel the milli. Now we do get molarity of this calculation, 0.0250 molar. Okay, so then that's the concentration of this A2 minus. Then the next question for you is, how is it going to behave at this point? You go, what is it? A2 minus and what? It's a conjugate base, right? So that's the conjugate base, or that's the most basic form. How does base behave? I think we know that. How does base behave in aqueous solution in water? So it's going to accept the proton and then produce hydroxide, right? So this will be Kb1, right? Okay, so since it's a base, and then we just calculate its concentration, then now we can set this up by use a shortcut we know. Okay, so then we'll have x squared over 0.0250 minus x equals to Kb1. Do we know Kb1? Well, we can calculate by using Kw divided by Ka2. Remember the relationship. Okay, so now I'm going to actually plug in the value over here. That's going to be 1 times 10 to the negative 14 divided by 2.01 times 10 to the negative 6. This value was given from the question. Okay, so now you do the calculation. That will be 4.98 times 10 to the negative 9. Okay, and then this is the setup. Okay, now this case, small approximation definitely works, right? Okay, so we can solve that x equals to 1.12 times 10 to the power negative 5 molar, which equals to the concentration of hydroxide. So of course we can calculate POH equals to 4.95, then calculate pH by using 14 minus 4.95, we'll be getting to 9.05. Okay, so this is the pH at the second equivalence point. Okay, almost there. One last one, right? Okay, one last one is what? When you get 55. Okay, So when VP equals to 55, and we know this is after equivalence point, which means you have excess amount of this base. Okay, so again, since all the acid turned into that conjugate base, which is weak, and then the excess amount of the strong base you're adding, that's going to be predominant in solution, the pH of it, right? So you just need to find out the excess amount and how much we have excess amount, right? We put in 50 ml, 55 ml in, 50 went into, right, reacting with that weak acid, and then the leftover or the excess amount is 5 ml of this base. Okay, and then we know its concentration. We'll be able to calculate the excess amount is concentration. So then you're gonna use 5 multiply its concentration divided by the total volume at this moment. What's the total volume? That will be the acid is 50 ml. We're adding 55 ml of the base, right? Do the calculation, get 0.00476 molar. Okay, so then this concentration of hydroxide, of course, we can calculate POH 2.32, and using 14 minus POH, then we get 11.68. Okay, so then that's after equivalence point, and then after all of this, we should be able to do this titration curve, right? VP is ml, then the pH, of course, as I said, for our assessment, right? So as long as you give me how it's supposed to look like, that would be good. Okay, so of course you can label this properly. Okay, so just say here's the 2, here's 10, 20, 30, 40. I'm just roughly doing it in case, of course, please, right, take your time that you do the proper. Right, mine's not the prettiest, but let's try to show, right, the buffer. Then you have. I'm not doing it at the correct ratio at all. Okay, sorry about this, but okay, roughly it's gonna look like that. You have 2 first equivalence point, and then around over here, right, 20. It was 25, right? Okay, so around here you get a increase, and then you have the second equivalence point at 50, right? Okay, so roughly, okay, definitely not the best. Okay, but then this is the example for how you're gonna do a diprotic titration. Hopefully this is helpful, and then that's it for this video.